right? So this is about working with hashing. So the last topic in your syllabus is like B plus tree. So B plus tree is a balanced binary search tree. So why do we study a data structure B plus tree in DBMS is that it can be used to store information in a multi-level index format, right? So you have first level of index in the memory, the second level of index is present in the hard disk, right? So whenever the information increases, the storage, like whenever the information present in a table increases, we cannot have only a single index file to retrieve the data in an efficient way. So we go for multi-level index. So multi-level index can be represented by means of a B plus tree. So B plus tree is a balanced binary search tree. So what do you mean by a balanced search tree, binary search tree? So it ensures that all leaf nodes remains at the same height. So in B plus tree, we'll be using the leaf nodes to store the actual data pointers, right? So the leaf nodes will be storing the actual data pointers, and they are linked together by means of a linked list, right? So the advantage of B plus tree is that it can support random access as well as sequential access of information. So we'll see an example, maybe next class or something. I will see an example for working with B plus tree. So as of now, you need to know that it's a balanced search tree. It can be used to implement multi-level indexing in a database management system, right? So one minute, I have a call. Right. So we'll study some theoretical foundations about B plus tree in today's class, and maybe we'll work out with B plus tree maybe in the next class. So B plus tree is a balanced binary search tree. It can be used for implementing multi-level indexing. So B plus tree ensures that all the leaf nodes, they remain at the same height. So again, in the B plus tree, the leaf nodes are linked using a linked list. So data is stored in the leaf node and they are linked using linked list. So a B plus tree can support both random access as well as sequential access of data, right? So regarding the structure of the B plus tree, every leaf node is at equal distance from the root node. So it's a height balanced tree, right? So the B plus tree is of the order n, where n is fixed for every B plus tree. So a B plus tree may contain internal as well as leaf nodes. So leaf nodes are used to store the data. So regarding the internal nodes, an internal node of the B plus tree can contain at least n by 2 record pointers, except the root node. At most, an internal node of the tree can contain n pointers, right? So generally, whenever you have an internal node in a B plus tree, it should contain at least n by 2 record pointers. At least n by 2 records should be there. And leaf node of a B plus tree can contain at least n by 2 record pointers and n by 2 key values. And at most it may contain n record pointers and n key values, right? So the internal nodes we have studied, it should contain n by 2 record pointers, and the leaf nodes also it should contain at least n by 2 record pointers and n by 2 key values. And at most it can contain n record pointers and n key values, right? So every leaf node of the V plus tree contains one block pointer p to point to the next leaf node, right? So I think that's it about B plus tree, but I will solve a problem maybe in the next class, and I will explain B plus tree, right? So B plus tree is a efficient technique for implementing multi-level indexing. So it's a height balance tree, right? So we'll be storing the information only in the leaf node, and data in the leaf nodes are linked using a linked list. So B plus tree can support both random access as well as sequential access of data. So regarding the internal nodes, it can contain at least n by 2 record pointers. And regarding the leaf node, it should at least contain n by 2 record pointers and n by 2 key values. And at most, a leaf node can contain n record pointers and n key values.